Hello and welcome to this review lecture on biomems and microfluidics for lectures 29 through 33. Now, in this section we are talking about first the how the Navier-Stokes equations can be simplified greatly with respect to incompressible flows, and assuming that there is a constant viscosity taken in these equations, and then finally arriving at a very abridged formulation of the Navier-Stokes in terms of indices, where we talk about the variation along the rows and the columns of all the three dimensions, the equations in all the three dimensions of the Navier-Stokes as derived earlier, and then we assume both a distance scale and a velocity scale, and then assuming these two scales and putting them back into the indexed equations in the Navier-Stokes, we are able to actually get a situation where we can have a very small nominal value Reynolds number coming out of the equation in a manner so that it becomes time independent. Okay, so the final formulation that we arrive at here is that the pressure gradient which is there, that is del P star by del xj star, okay, where these P star and the xj star are basically the scaled down pressure or the scaled pressure, or the pressure scale and the distance scale, and this becomes equal to the del 2 ui star by del xj star square. So, therefore, the shear stress part of the equation is proportional only to the pressure gradient, thus removing the time domain totally out of the equation, and that is what typically happens when we talk about low Reynolds number flow in micro mixing, etc., where there is really no time dependence. If you are having a mixer where there are, let us say, two flows flowing together, and if you just go back in time, you would be able to extract the two flows as is, because there is hardly any mixing because of any turbulence related issues at such a low Reynolds number domain. So, in a way, practically whatever we have derived with scaling down is also seen at various levels when we talk about microflows and microfluidics. This lecture also includes a section dedicated to micro mixers, where we talk about the various generations of micro mixers, like the first generation T type micro mixers, the second generation out of plane in plane type micro mixers, and then finally the third generation, where there is a rotation, the rotational behavior of the flow, which creates diffusion pathways of one fluid into another by virtue of that. And what we really learn is that most of the mixing at this particular scale, because there is hardly any time dependence, and at a low Reynolds number there is hardly any eddies or vortices created or turbulence created. So, the most of the mixing is actually diffusional in nature, and with that we actually compare the diffusion time scales with the resident time scales and see how we can vary the fluid paths in a manner so that the time scale increases as far as the resident time scale is concerned, and it can somehow be able to match the diffusion time scales, which are in any event huge because of the very low diffusion coefficient of the fluids in micro scale mixing. So, thereby we make the various design constraints for passive and active mixers, talk about different lamination, sequential and parallel mixers, and then we also look at some of the mathematical models of how to handle the mixing, how to predict the mixing time, the mixing path length, so on and so forth. We also look into details of how some of the micro scale control mechanisms can be executed in an engineering manner by looking at micro valves, micro pumps, and that both active and passive. We talked about peristaltic micro pumps, for example, how to design the particular micro pumps, and then also talked about pneumatic and thermopneumatic micro pumps and micro valves. In a nutshell, we have summarized that what are the applications of such scaled down fluidics, which we learned from the Navier-Stokes analogy earlier, into the realistic physical scale, where we are talking about experimental validation of some of those theories. So, in a way, in a nutshell, what the lessons that we learn is that microflows are very low Reynolds number flows, they are typically time independent flows, and then most of the mixing at the micro scale takes place through diffusion driven mechanics, and then also the surface forces become very predominant, where it is felt increasingly that if you actually initiate the dynamics of flow through more surface initiation, it is a much better energy efficient means than going by the volume or pressure driven mechanisms as earlier and as normally takes place in the macro scale. So, in a way the behavior, the flow behavior at the micro scale is quite counterintuitive and different with respect to what an otherwise trained engineer in the fluid mechanics would envision in the macro scale. Thank you so much.